Well, let's continue with our investigation of Liouville space. I want to just I want us to remember what we figured out last time, which was that we could postulate that there was a Liouville space time evolution operator that evolves the density from T0 to T, which we could then plug into the Liouville equation in Liouville space. And when the Hamiltonian is time independent, the Liouvillean becomes time independent, and then we can just solve we can write down directly the time evolution operator in Liouville space, remembering that this is times, not a function here. Okay, what else do we know? We know that the u t0 t0 or any two times is the same. All right, so what we'd like to do now is a couple things that we can do is we can switch back and forth between Liouville space and Hilbert space, because it's certainly useful to do that. And so one way to do that is to remind ourselves that in Liouville space, u of t t0 on rho of t0 has the equivalence in Hilbert space of doing this, which is what we started with a very long time ago. Okay, and so for example, if we set t0 equal to 0, just for the simplicity of the notation, then we can write down that e to the minus I over h bar L times t now of rho 0 corresponds to e to the minus I h times t over h bar times rho of 0 times e to the plus, because it's dagger, I times h times t over h bar. Okay, so just trying to make it clear what happens when we go back and forth here. All right, so what we're going to do now, what is the standard steps that we've done, right? The standard steps that we did in Hilbert space was we said we have a Schrodinger equation, we have a postulate, there's a time evolution operator, we put the time evolution operator back into the Schrodinger equation, got an equation of motion for the time evolution operator, we could solve it formally, then we realized that the time dependence of the Hamiltonian is non-trivial, then we have to do something like a Dyson series. We use an interaction picture to formulate the problem in terms of a piece of the Hamiltonian that we kept intact and the other part that we could expand in a series and then truncate. We're going to do exactly the same thing. But one of the key steps in there, in the Hilbert space case, was that we always wanted to have a bit of the Hamiltonian that we could treat like, it was u0 for our Hilbert space case. And the idea was that we had a Hamiltonian that was solved already. Something like this, right? Where we already had a reference problem that we knew. Some energy levels, if you want to think of it like that. And then that gave us a basis, right? We have the basis of whatever these eigenvectors are. We want to do the same thing, but for Liouville space and the Liouvillean operator. Now, what is the basis in Liouville space? Remember, the basis in Liouville space is, instead of a single vector like this, now the basis in Liouville space will look like an operator in Hilbert space, right? So we can write it in any different number of ways. We would have written something like this before, which we can then rewrite into Hilbert space like JK. All right, so what we want to do here is we'll use the same kind of basis like I wrote here, and we're going to write the Liouville. We're going to look at what the Liouville operator does on these things. All right, so for example, I could write phi n, phi m, or nm, whatever, right? And this would correspond to the Liouville operator phi n, phi m. Right, what we want to do is we want to figure out what this does. Remember, the Liouville operator in Liouville space, sorry, the Liouville operator in Hilbert space, L, is equal to H, the commutator with that thing. All right, so we're going to do this in Hilbert space, like this. All right, so let's see what that is. So that is H phi n phi m minus phi m. Sorry, the order of the operators doesn't change. It's just the order of the two. So this will be still phi n phi m h. All right. So now what we can do is we can take advantage of the fact that the Hamiltonian is Hermitian. What that means is the operator acting to the left would normally act to the left as a complex as the Hermitian conjugate. Here, of course, it does, but the Hermitian conjugate is exactly the same thing. So this is going to give us En. We can put zeros in here if we want, just to remind ourselves that eventually this is going to be like the zero Hamiltonian. Gives us back to phi n again, of course. And then we're going to have this is the same as this. So we can factor out the m that we'll get here minus, the minus comes from the commutator. Okay, so what do we notice here? What we notice is this vector here, this operator, of course, is the same one we started with. Interesting, huh? So now we can translate back into Liouville space. We recognize that L operating on phi n, phi m equals En of 0 minus Em 0 operating on that same Liouville space vector. Remember, the difference between Liouville space and Hilbert space is, in some sense, nothing other than a way of repacking the same information. All right, so what this is telling us is that this is a basis vector in Liouville space with eigenvalue En minus Em. Okay, so this is hopefully inspiring you to realize why Liouville space might be important in spectroscopy. Spectroscopy is largely about determining energy level differences. Well, here we see that there's a Liouville operator operating on one of its eigenvectors of the Hamiltonian that it corresponds to, gives us back one of these energy level differences, right? A gap of energy. That's going to help us manage spectroscopy quite a bit easier. Okay, so let's finish this up. We have that the Liouville operator operating on what it turns out, one of its own eigenvectors, gives you back an eigenvalue here. Now, this energy level difference is no problem. We can keep it like that. But we've seen things like this before, right? Where we had an energy level difference that we decided to write in terms of a frequency. So how do we do that? We know that energy divided by h bar is going to be a frequency. So let's just define a frequency, omega nm, which is exactly equal to this, En of 0, Em 0 divided by h bar. That turns the Liouville eigenvalue problem into the following. This is going to be h bar omega nm phi n phi m. Now we see that this is, the eigenvalue, okay? And we've converted it into a single number. Obviously, we need to know two numbers to get this number, but it's an energy level difference expressed as a frequency or as an energy if you multiply by h bar. So what we can do now is we can take u and express it in a basis, all right, a basis of the eigenvectors of the Hamiltonian that is responsible for time evolution. Whether it's Liouville space or not, it's still the Hamiltonian. All right, so we plug in what we have here, right? And so what we're going to do is we're going to put the u first. All right, and so then what does u do to phi n, phi m? Well, we're assuming, because we're starting out easy, that we have a time-independent Hamiltonian, of course. All right, so if we have a time-independent Hamiltonian, we're going to put this in. So this is going to look like e to the minus I over h bar L t minus t naught, operating on phi n, phi m, phi n, phi m. All right, well, what did we just find out? We just found out that phi n, phi m are the eigenvectors of the Liouvillean. So now we know what to do with a function of the Liouvillean. If it operates on its own basis, it does exactly what it did in Hilbert space. We simply replace the Liouville operator by the corresponding eigenvalue. Right, we'll do that next. Well, what is the eigenvalue? It's this, h bar omega n m. So this is going to be equal to e to the minus, now the h bar and the h bar here will cancel. So that's e to the minus I omega n m times t minus t naught. Back on this, what did I leave out? Okay, I left out the sum. Maybe you caught that. Both of these need a sums back. All right, so what you see is just like in the case of the Schrodinger equation, we have the Hilbert space is what I meant to say. We have a phase factor that is associated with the time evolution operator when the time evolution operator acts on a vector in its own space, its own eigenvector, one of its own eigenvectors.